Welcome everybody to the series of Inside It's OWL. Today we will present the project Easy as mentioned to you. And if I say we, that are me and my colleagues as presented already. My name is Maximilian Bauser. I am a research assistant in the Department Scientific Automation of the Fraunhofer IEM in Paderborn, working on the topic Trusted Machine Intelligence. And for further introduction, I want to first of all give the word to my colleagues that are presenting to you today also.
Yeah, Maximilian, thanks. My name is Heiko Stichweh. I'm the head of the Department Innovation, and the Department Innovation is responsible for making research projects together with universities, partners, and so on, and to get in touch with new technologies which are relevant for our company and, of course, for our customers.
Yeah. Thank you, Maximilian. I'm Simon Michalke, Innovation Manager at Dog1, the Digital Innovation Lab by Lenze Group. And we build business models specifically revolving around machine learning for the future of Industry 4.0.
Okay, so thank you very much. To conclude the short introduction, I want to give you a small introduction into what we are discussing today. So, Simon, please, can you mute? Thanks a lot. So today's event is divided into different parts. So first of all, I will start with a small overview of the project Easy itself and in general. So what we are facing in that project, what the challenges are, and yeah, what we want to do in this whole project case. Then we will go a bit more detail into a specific use case, the predictive maintenance use case. It's one of all those use cases, or all in all, we have 3 use cases in this project I will describe furthermore. And that is then done the introduction by Mr. Stichweh. Then I will focus on the part of trusted machine learning. And finally, Mr. Michalke will give you an overview of the IoT or architecture and infrastructure we want to use to set up our machine learning algorithms, followed by a small conclusion. So to start with the general project overview, the question is, what is the motivation for all this? And today, all products, it begins with simple coffee machines or something like that, or even more complex plants like we have in industry. It's always that they become more and more complex by multifunctional features and so on. And in generally, a mechatronic product becomes more complex. So this leads to new challenges for companies and especially also for their employees. So for machine operators, it's typically not that easy to understand the modern technical system completely with all functionalities and dependencies, and thereby results of actions in terms of maintenance or, for example, machine setups are less predictable. So to sum up, operators are not able to make the right decisions at the right time and in a target-oriented manner anymore. So this is the reason why we are facing some of these challenges in our project. So it's typically the way that prediction of a plant behavior is required, but that typically also needs high efforts for calculations. And if we do that calculations in the cloud, a high amount of communication and data transfer is necessary. So edge computing or embedded computing is a solution that can face this challenge because we can run the algorithms we have directly on our devices and not in the cloud anymore. So that we have all our algorithms and functions down to the shop floor and run that machine learning algorithms directly on programmable logic controllers or something comparable. So the goal of our project is the development of those AI algorithms for execution on embedded or edge devices. And therefore, we of course have to consider all those limitations in terms of resources we have for calculations. And the big aim is to validate that approaches in different use cases we have. So when we are talking about the project in January, to give you a smart overview or small overview, the project is for about 3 years. It started in October 2020 and will go on to 2023. We have defined 8 work packages in 3 use cases. And if I say we are 5 different project partners. So they are shown here. On the German side, we have the Fraunhofer IEM and also the company Anchorway and Lenze. And for another use case, the company Duispol. And on the Canadian side, we have our partners from Canada, the UVic, the University of Victoria, and the company Anti-Wist. They work together on a further use case. And all this is supported by the Federal Ministry of Education and Research in Germany and the National Research Council of Canada. So here we have our work and time plan. We don't have to look into that into detail. What I only want to show is where we are right now. So we are in the middle of the project. The detailed plannings go on and on. So the most initial steps are made, and now we are going into more detail for our use cases actually. To give you a small overview of the use cases we have. One use case is the predictive quality use case. It's together with Fraunhofer IEM and the company Duispol about the RoboWrap, a fully automated profile wrapping machine. And there we are analyzing the impact of roller wear and tool characteristics in this wrapping process. So therefore, we want to set up an intelligent algorithm that is able to react on roller wear and on the specific tool characteristics and to predict how this can affect the quality. And our aim there is a demonstrator for AI-based quality prediction on an edge device. Another use case is the predictive maintenance use case with Lenze and Anchorway. So there we want to focus on condition-based maintenance of stacker cranes. So that mainly means fault prediction in the high bay warehouses for that stacker cranes. And a very important aspect thereby is the integration of expert knowledge to improve the data efficiency and the algorithms efficiency. Also here we want to have a demonstrator for multi-sensor based intelligent fault prediction. And the third use case we have is mainly where our Canadian partners are working on. It's a manufacturing execution system where they also build up digital twins to improve the performance. And they have several agents. They have to coordinate between them. And yeah, the main goal of this use case is an effective AI-based decision support system for an intelligent manufacturing execution system. And those use cases are related together by a regular exchange and discussion. So we have regular meetings where we discuss our problems and challenges we have and support each other by finding solutions and go the next steps. And what we want to do now is focus more on a specific use case, so go more into detail for one use case, and that is the predictive maintenance use case. And therefore, the introduction will be now made by Mr. Heiko Stichweh from Lenze.
Maximilian, thanks for the introduction. And I would like to introduce the use case for predictive maintenance. And therefore, I would like to give you an idea what a stacker crane is. One moment. Okay. A stacker crane or automated storage and retrieval system is the main part of a full automated warehouse. And here you can see a stacker crane system for a container or totes. So stacker cranes are able to pick up totes or containers or pallets or to store them. You can use them in high bay warehouses. So it's a space saving solution. And this is the biggest benefit, a full automated solution. So it can be directly coupled to MES and ERP systems. And therefore products that are needed can be sent to production or to the final customer or can be stored. Here you can see a second stacker crane system for pallets. And yeah, you can see that it is comparable to the container solution. As explained, these solutions are fully automated and lots of goods are inside one ale. So why is this topic so important for predictive maintenance? The reason is when one of these stacker cranes has a defect, all goods that are stored inside one ale can't be reached and can't be used for production or for sending them to final customers and so on. So the challenge for the plant operator is that he has to secure high availability of warehouses and a high overall equipment efficiency. And therefore, we are focusing in this project on an increased availability and a better machine transparency, so a better transparency about the condition. And we would like to decrease inspection time, maintenance efforts, as well as downtime in the production. And in the beginning of the project, we take a look on lots of service documents, lots of inspection documents, and we found out that mostly the relevant parts that leads to failures and standstill times are mechanical part of the application. So normally it is not the motor or the inverter which makes the speed control, which leads to an unplanned standstill time. Normally these are belts that lose their tension and fail in operation. Here you can see some driving wheels. Of course, we have big wear here on these driving wheels. They can slip. Here you can see guiding rails. Of course, they are here. We have also some wears. And inside the drivetrain, there are lots of bearings. There are some gearboxes, gears, some brakes, and all these parts there we can see wear, and we would like to measure the condition of these parts. Of course, today there are existing solutions. Most of them are based on vibration and oscillation analysis, so you have to integrate more components. Our idea here in this project is to use the existing infrastructure. So if you have a stacker crane application, which can be seen on the left side, then the traveling unit and the hoist unit are driven by speed variable drives, which consist of motors and inverters. And these drives can offer a lot of data like speed, like torque, even with high frequency. And based on these data, and of course, our domain knowledge and maybe some additional sensors, we can realize condition monitoring solution in order to make predictive maintenance available. That is the idea. And Lenze is producing those drives and inverters and also software components. So here we have a good opportunity to offer data, to offer functions, to offer also domain know-how. One moment. So, of course, we would like to test the solution under really operational conditions. And therefore, we would like to integrate the results of the project easy in the so-called Lenze Mechatronic Competence Campus. What is the Lenze Mechatronic Competence Campus? It's a new building, a new place for production and for manufacturing in Extertal. And here we have a really high automated storage system, which is totally new and will be active in autumn of this year. And we have also here a new facility where development and productions are near to each other, and where we would like to enable agile interdisciplinary development in teams in open plan areas. And this project here is a really good starting point also for these activities. Inside this new mechatronic competence campus, we have 8 storage and retrieval machines, 5 for pallets, you can see them here, and 3 for containers. So we have at least 8 of them and comparable types. So we can get lots of data of these types in order to train our AI and of course to test the system. Of course, our operation will not be amused if we integrate some weird parts here in order to learn how a weird part will behave. Therefore, Lense has also realized a testing possibility in our laboratory. And here you can see a small stacker crane solution. It's a model, which is nearly comparable to the big one, but smaller. And on this model, we are able to reproduce and reproduce a typical weir patterns. And here we can design, train, and test the algorithms, and of course also the infrastructure. How is it possible? Here you can see more detailed pictures of our testing system. Inside the system, we have the opportunity maybe to change those driving wheels and to insert some weird or damaged driving wheels so that we can measure the behavior of older driving wheels. And of course, we can change the backlash of guiding wheels and so on. And as explained, we can use the data coming from all drive system from our automation solution, as well as we have the possibility to integrate further sensors. So I think we will show you some additional vibration and acceleration sensors we are working on and we would like to integrate. These can be also integrated in the system, and the data can then be sent and offered to our AI algorithms. With this small overview over the use case, I would like to hand over to Simon.
No, so I will go on. Thank you.
Sorry.
Thank you, Mr. Stichwe.
To Maximilian, yeah.
Okay, yeah. So you have already talked about the additional sensor bots. So I want to to start into the part of trusted machine learning for predictive maintenance by showing you first of all, as an introduction to all this, the architecture we have. So this is a more simple picture to show you what data we have and how some components communicate with each other. So first of all, we have the Lense inverters, and from those inverters we get really with a high resolution information about speed, motor torque, current, voltage, and so on. So all those control information for the stacker crane, for the drives. And of course, this is needed to actuate the stacker crane. And in the real behavior and also on our test bed, we want to do reference drives. So with a specific velocity and acceleration, we want to accelerate the system to get reference drives. Also, those data can then be sent from the inverters to the edge device we want to use. There's a Lense software running, and there we want to integrate by Docker containers our machine learning models that are then able to make predictions on the actual system behavior. And as Dr. Stichwe already mentioned, we plan to use an additional sensor board. So this is shown here. It's a microelectronic sensor board out of the low-cost area we want to integrate to additionally to those inverter data, get information about vibrations and acoustic emissions and also maybe the temperature. But we are relatively optimistic that those data from the inverters, those motor data, are relatively we are relatively optimistic that we can use them even to get good results for monitoring of mechanical components. The sensor board is only an additional feature with where we hope that we can get a higher accuracy by fault detection. So then from the edge device, we can send data into the cloud to store all those big amounts of data we will get over time. And in the cloud, we can do machine learning algorithm, but then we can compress those algorithms and deploy them back on the edge device where they can run in real time. And from that edge device, then we can give predictions to a server or a host computer, for example, to an operator to directly get the information. And this will work even if the connection to the cloud has failed if we have already deployed the model. So let me come to the introduction of machine learning in this case. So for those of you who don't know what machine learning is about, it's a subdomain of artificial intelligence. It's about algorithms that are able to learn desired input to output behavior in an automated way from data. So in difference to traditional approaches that are typically by defined rules by human beings, the rules for decision must not be identified because they are extracted automatically by the algorithm. And there are several application areas, for example, image classification and segmentation, also control tasks, and of course, what we are talking about here, so predictive maintenance, or in general, condition-based maintenance. So the benefits are, for example, that we are able to identify hidden trends and patterns with high complexity, and also about multidimensional and multi-variety data. So this means the algorithms are able to detect even more complex dependencies that a human being by manual analysis cannot extract from the data. Furthermore, it's the next step of automation because all this is a more automated way to do predictive maintenance, and it's also very dynamic in terms of adaptability to new data or new use cases. And of course, there are a few challenges. One of the most important ones is data acquisition. So to get not any data, we need really defined data. We need the data that are relevant for our use case and also in an adequate way. And another challenge is the interpretation of results and decision making. So those machine learning algorithms have a black box character, and this directly leads to the next challenge, the error susceptibility. So we have a lack of safety if we do not have enough data, or if there are any gaps in the data we have, and then we want the system to predict for such a data gap in future. So this can give us unpredictable results for prediction that are maybe really failure or failable. And of course, we have the computational efficiency that we have to be aware of. So the elements of a condition-based maintenance framework, that means condition monitoring to sensor data, are shown here on the right side. First of all, we have our physical system. Then we can do data acquisition on that system. A very important step is also pre-processing of those data, so regarding outliers, resampling, and so on. Also the feature extraction, so maybe manually extract relevant features from those data, and then do diagnosis by, in these terms, a machine learning algorithm. So that means fault detection, isolation, and identification. And in the next step, also do prognosis, which means predicting how the condition of the system will change and also what the remaining useful lifetime is. So how long the system will be able to run furthermore, and also this for subcomponents. And then we can make a decision in terms of maintenance planning and reliability control and react to our system. Typically, in the case of condition-based maintenance, we use supervised learning, which means that we have labels available for the data. And label means a feedback about the system health, so that we know for every data we have, how the system condition is like. And then we can set up a machine learning algorithm that is shown here in a simple structure. So when we have training data and extract features, for example, give also the label to the machine learning algorithm, we can use an optimization to get a machine learning model. And then for new data, we can use this machine learning model in an online application to predict new outputs and make new predictions. And the question is, what is this label about? And in maintenance, there are two principles we have to look at. First of all, the label has to be complete, so it has to contain all the relevant system information about system conditions that should be predicted in future. And another aspect is the granularity of the label, because you can only distinguish between conditions that are evident from the label. So this is a kind of resolution of the prediction we can make. And there we can, on the one hand, have the granularity of fault description. This can be shown, for example, here by this image for a staker crane, where we have several sub systems of the whole staker crane and also components of those subsystems. And for each component, we can also define different wear mechanisms or defects. So fault types we want to distinguish between, and this has to be a part of the label so that we can distinguish. If we don't have a label at such an it's a top-down approach. So if we don't have the label here on the lowest area, we can maybe only make predictions for a whole component in general or a whole subsystem in general. So this is something you have to be aware of if you want to do condition monitoring by label. And also we have the granularity of fault progress, which means how to describe the faults on the time axis. So for condition monitoring, we can have binary or discrete descriptions, but also continuous. Binary, for example, would mean only distinguish between health and defect. Whereas continuous would mean, for example, a percentage health of the system. And on the other hand, we can also consider the time horizon. So then we are able to do predictive maintenance on data. And this means always have a reference to the time of failure. And here we can also have binary, discrete, or continuous states. But of course, the most, or the best information would be the continuous one. So that would mean a remaining useful lifetime for the system. And this together makes the granularity of the label. And a very important aspect is what are sources for label acquisition. So there we can use digitalized maintenance or service reports and also general information about component replacement. And also it is possible to measure where describing variables. So for example, by sensors, but also manually by operators directly at the system. That are the opportunities we have. And if we don't have a label, this is important to say, it's then we can not predict directly faults, but we can do anomaly detection. So detect whether the system behavior changes from the typical behavior. So let's now come to approaches of Trustful AI. This is something we are focusing on in the project, next to bringing the algorithms to an edge device. So typically in maintenance, we have the problem, first of all, that we have lack of data. So for example, missing labels or sparse examples, because system like a staker crane does not fail every day. So we do not have much data about that. And also the data balance is such a challenge, because if you remember such a system, 95% of the time it will be healthy, and only the rest 5% are really relevant for failure mechanisms. And this healthy to failure ratio we have to consider by, for example, balancing our data sets we are learning on. And also we have the case or the topic reliability of the prognosis. So the traceability of the decision making, what can be really complex if we use AI algorithms. And also a question is how to deal with data gaps and uncertainty. And a solution of that is informed machine learning. So there are some or three areas we can define for that. First of all, we want safety of the prognosis through self-evaluation. That means a safe training of the algorithms and a safe usage also. For example, by considering and analyzing data gaps. Also, we want to remove the black box character by understanding the process of decision making, which comes to the topic of explainable artificial intelligence. And on top of that, there is the point adaptability. So that means influencing the algorithms for wished behavior. And all this can be seen in the context of hybrid modeling. So hybrid modeling means feeding expert knowledge to the system to make use of the rules from the expert knowledge and to support all this decision process and to understand the system and how to affect it, the AI-based system. And concepts for decision support in machine learning are, for example, synthetic data by model or by testbed. We have seen the testbed in the beginning, Dr. Stichwey showed us. So we can learn on that data and make a transfer learning approach to bring that machine learning algorithms we have learned on the testbed on our real application. And also to support by hybrid approaches by integrating expert knowledge, for example, by physical models. And the idea of hybrid modeling is shown on the right side. So a really data-based approach would look like this one we have on the right now. We have training data, we train the model, and we make prognosis on our measurement data. And classically, it's the way that that model-based diagnosis techniques were used, which can be seen in a parallel way. But if we talk about hybrid prognosis, we want to combine both approaches to benefit from the advantages of both. So on the one hand, the ability of machine learning to automatically identify complex patterns and hidden relations, and also the model-based or the physical model-based approach to make all this more robust and reliable. And those integration of expert knowledge can look in different ways. So we can have a parallel approach where we have machine learning and a physical model next to each other, and their outputs can then be fused by a decision fusion system to make a prediction. Also, we can have some serial or parametric approaches, for example, by a physical model that gives output like, for example, residuals or parameters to the machine learning algorithm in addition to the input data we measure. And then we can predict. Also, we can change this this system that we have the machine learning before the physical model, so that the machine learning supports the physical knowledge where we don't have physical rules or something like that that we know for some subsystems, so that we can integrate machine learning in the physical model. And the topic we also have talked about already is this transfer learning approach where we can give control signals to physical models or also to a test bed we have, and then use this to learn the machine learning algorithm on that data, and then use it on a real system. So these are approaches, and what we are focusing on in our use case is on the one hand, the serial approach with physical knowledge before machine learning, and also a kind of making use of transfer learning from our test bed. So the procedure in our project context finally looks like this. So here we have a hybrid architecture we want to try out on our data. So input here is already pre-processed time series data where we have resampling done and so on. Then we can do domain transformation. So we are expecting the frequency domain as mainly important for getting those faults we want to have to extract them. And then we get this feature extraction layer by a convolutional neural network. It's a special form of a neural network that is able to find features and hidden relations in our data, and also is able to take a look on multivariate data in common. And also we can do manual feature extraction by, which is the first kind of expert knowledge that we give into the system. And then we also want our model-based diagnosis parallel to that, where we can calculate residuals or parameters by physical law, and all this we can give to a feature vector, and then make use of a more simple neural network as a classificator for giving us predictions about the system's health and how long it will be healthy anymore and when it will fail. Last important point in this case is the realization on edge devices. So of course on the edge devices we have limited computational power available, and what we have to do on the edge device is writing new measurements to a database, to an InfluxDB in this use case. And we want a direct analysis by our machine learning algorithms as a Docker container. And then we have also to have a look at the real-time capability of the physical models we want to integrate. They can't be too complex and too calculation affordable. And another step is the optimization of the trained machine learning models. So there are specific techniques that are part of research actually. It's, for example, pruning and quantization, and for example, TensorFlow Lite is a software that gives us those techniques as toolboxes where we can make use of. And the aim, of course, is the direct analysis and prediction of the results, and all this should work on the edge device. And of course, we have to focus on our algorithms that they are safety and reliable, and also that we have a robust communication by those high sampling rates we have by measuring vibrations and also those oscillations. So now I will finish my part, and then I will give the word to Mr. Michalke to come to the general IoT infrastructure where our algorithms will run on.
Yeah, thank you, Mr. Bowser. So let's talk about IoT and software architecture. Generally, we have to divide between two systems. So here we look at the experimental setting applied in MCC, and this will be a little bit more loaded, of course, than the embedded device. We will look at the shop floor at the different devices we employ. These are usually these are Lancer products, but you may also use other products. We use protocols such as OPC UA and MQTT. So this is basically an open system with very secure endpoint. Then we have our core system with 6 different Docker containers, and these Docker containers house different services. So 2 services are the main services. The AI trainer allows us to train models based on the pre-processed data we extracted from the machines. This also includes sensor data, and the AI runtime allows us then to pass basically trained models to the AI runtime and utilize these models on preprocessed data directly from the machines. Of course, we aim to make this run on the embedded device, but now let me emphasize that again. We are looking at the experimental setting and at the MCC, so the Mechatronics Competence Campus of Lancer, where we want to extract data to really get high quality data and utilize the experts, our colleagues on the shop floor, to inform our decision making and inform our models. Once we have the models up and running in the AI runtime, we are also able to send them to a front end. And of course, we want to make it available both on offices and on the shop floor. So we might use the X4 OpenIoT platform that Lancer already employs to stream the information about with the predictions, with warnings, with reportings, with monitoring tools to our colleagues on shop floor and in their offices. There you go. Let's look a little bit more closely on the shop floor and the hardware architecture. So the stacker cranes so we have 8 stacker cranes. These are powered by drives, of course, and then connected to inverters and PLC controllers, employing EtherCAT as communication protocol. We then go to the edge device. This could be a Lancer device or another device where the Lancer Lean Data Hub is running. sends out MQTT data via MQTT or OPC UA protocol via a secure Wi-Fi connection to our data center. And now we get to the software system, where the data is handed to via MQTT or OPC UA data. This includes drive data and sensor data. This could be sensor data, as Mr. Bowser explained, about vibration, acoustics, and temperature, supporting the drive data we already have. In this core system, these services are employed in Docker deployed in Docker containers for easy deployment. The data manager will receive the data. This is an independent service, so it doesn't matter if it's a Lensa product or another product, that the information is handed to the data manager will allow us to conduct basic data manipulation to save the data to an InfluxDB, adding, for example, text like data type, or assigning names to measurements, making it easier for us to see where the data is coming from. Is it from this machine, that machine? Is it from this building, that building? And these informations will be saved in an extra Postgres SQL database to support the data selection process. So then another Docker container, the AI manager, which orchestrates all the data and also communicates with the AI trainer and the AI runtime. I will come to in a second. The AI manager will send a pull request to the data manager, extracting the time series data we are storing in InfluxDB. And then we add labels, we add hyper parameters to actually train the models in the AI trainer. The AI trainer will employ a data preprocessor, adding normalization, standardization, segmentation, feature extraction, and dimension reduction before the model is passed to the AI builder, then actually training the algorithms we have selected in the AI manager, and putting out the results. If we employ unsupervised models or semi-supervised models, we may use the data post-processor to evaluate the data using additional labeling manually. The results and the models will be saved in MLflow, a database specifically tailored to saving machine learning models and results. And then via the AI manager, we again have the possibility to access these models to either deploy them in different runtimes. So if we have a system in Germany and maybe one in Austria, we may utilize these models in different systems via the cloud. So this is basically the trained model on historical data, which is then passed to the AI runtime. And the AI runtime, of course, needs real-time data to unfold the potential of it. So the data manager has a WebSocket the AI runtime can communicate with to enable the data stream, and then this will be preprocessed just as the AI trainer will preprocess the data. And the AI runtime will then apply a real-time classification regression to identify anomalies, based on which it will compile reportings, warnings, and monitoring applications. These will then be made available via our open IoT platform X4 on different devices on the shop floor or the offices of our colleagues. Sounds pretty large. If we look at the 6 Docker containers, if we look at the libraries we might employ, we employ machine learning in our project. It says AI trainer. We plan to deploy different or embed different libraries, data science libraries. So this system is then running in the MCC, allowing us a plethora of things. But in order to make it work on an embedded device, of course, we need to simplify it. We need to look at what is needed, what is performing best, and then compressing it to the minimum to make it work on an embedded device, right? So while this is a pretty mighty software architecture with a lot of benefits, this is our experimental setting to test the decentralized architecture for database condition prediction. We then need to employ the architecture and make it feasible on an embedded device. This is the core challenge here. But still, the experimental setting, despite the pretty much the higher weight of the software application, will help us to acquire and improve our data and will enhance our overall model quality. Even more so because we were working in a real life scenario where we can conduct validation and integrate through expert knowledge of our colleagues on the shop floor. And then, of course, next steps are needed to make it work on the embedded system. We need to deploy a light version of the architecture on the testbed, test how it is going, what limitations of the resources really are, where we can trim down from our little bit more bloated architecture, if you want to put it like that, and selecting only a limited number of data science libraries to reduce image size, deploying an optimized software architecture without the Docker containers because they have a lot of overhead if you just deploy 6 of them. So we need to see how many is feasible. Of course, this comes with easy deployment, but this is now easy embedded systems, right? So we cannot just look at what's comfortable. We need to just make it small, make it feasible on the embedded devices. Using light Python frameworks, for example, TensorFlow Lite or MicroPython would help making it work on these systems. So our goal in general, coming from this software architecture, serving as a reference in the MCC, allowing us high quality data acquisition, to coming to a reference model for decentralized embedded systems for machine learning, working on edge and embedded devices. Yeah, thank you for listening. I will just give you a short summary. So in the EASY project, we have started with the development of ML algorithms for database condition prediction. And what we really want to do is afford or support robust decisions through the integration of expert knowledge, even in our working systems. So the decision support is afforded by a model-based analysis and through the use of additional data and the knowledge transfer from our test bed, where we can just change reals, we can work with the different drives, just see how it changes, just evaluate how our models are doing to improve security. The next steps are clearly we need to improve the data acquisition, even from our real systems and MCC. We need to optimize our ML algorithms on this first data we extract. We need to validate it. We need to integrate expert knowledge, as I said, from our colleagues from the shop floor, the experts. And we need to compress the model so it fits on the embedded device while still integrating this decentralized software architecture. And then test how it performs. Thank you very much for your attention. I will just give you our contact information. I would be happy to have your questions. Thank you.